Hi, in this lecture we're going to talk about Chapter 7 on variances. And let's find the right place here. The usual assumption for all our regression models up till now has been that the variance function has been constant, sigma squared, or in other words, the variation in the errors are constant standard deviation for every observation. And in this particular chapter, we're going to talk about ways that when that is not true, what we might do about it. First thing we need to talk about is how we might express or communicate a variance function that is changing and how we might do that. Here we're going to suppose that the variance function, the variance of the error terms in the data generating process can change from observation to observation, and we're going to let them change according to a value wi. And these wi's are called weights. Whenever the wi's would all be equal for every observation, then you'd have a constant variance function. The variation would all be the same. And the pattern here is that when you have a bigger weight, the division, this fraction, is going to be a smaller value. So try to keep in mind that larger weights mean smaller variations. We have a typical model that's vector y observations is equal to an x matrix times a beta vector plus an error vector. And when the errors don't follow the same variations, we write this error variation matrix as sigma squared times w inverse. And w is just an n by n diagonal matrix that would have the individual w weight values on the diagonal. And when you have this kind of structure, it turns out that the right way to do estimates for beta is to minimize the residual sum of squares again, but that the residuals for every observation are weighted according to the appropriate weight wi. And that means we need to minimize this sum of squares. When you do that, you're going to get an estimated beta vector that is going to have a formula that will involve that W matrix. Remember that ordinary least squares estimates would not have a W matrix here or here, and so this is the modification for doing weighted least squares. And we're going to denote weighted least squares in this unit by WLS and ordinary least squares OLS. Basically what's happening in this formula is that observations that have a higher weight are going to contribute more to the estimation of the beta vector components than observations that have smaller weight. And so we are going to use observations unequally. We're not going to treat them all equally valuable. We're going to discriminate against some observations that have higher variation and lower weights. And we're going to use the more stable and more valuable observations, the higher wi's, a little bit more heavily. It turns out that both weighted least squares and ordinary least squares produce unbiased estimates. By that I mean that on average the estimate vector is whatever the true beta vector is in the data generating system. On average, both of these estimation methods will produce estimates that are hanging around the true beta vector. The important feature is this third bullet, that the advantage of weighted least squares estimates is they are typically going to have smaller standard errors for the beta hats than ordinary least squares will. And I think it should make some sense why this would happen, because we're using some of the information more efficiently. We're using the better data more heavily, and we're using the more uncertain data less heavily, and therefore we get better performing estimates. One very common example is where the response variable wi observation is made up of an average of a sample or a county or a state. And of course what we learned from introductory statistics is that averages have a variation that is dependent on how many observations make up the average. Just think about this for a second. If you take an average income of 10 people, the variation in an average of samples of 10 is going to be much, much greater than the variation in average for if you average 10,000 people's incomes. So you need to take into account of how many you're averaging, and that is denoted by n sub I, the number of observations that make up the ith average. And that means that, you know, if you're talking about the variation of an average, the variation of the y variable being an average, it's sigma squared over the number of observations that make up the average. And that implies that the weight for such a case is the number of observations that make up the observation, the average. And so data cases I that have higher weights or higher amounts of data that they're based on gets weighted more. And sample values that are made on smaller numbers of observations will get used less. Another possibility for the variance function is that the variance function is proportional to a predictor, like the predictor x. And so observations that have large x values might have bigger response variation than do smaller x values. And if this variance function needs to fit the model sigma squared over wi, it implies that wi, the weight for this case, would be 1 over xi. That's just solving a little inequality that x has got to equal 1 over wi, and so that means that wi is 1 over x. So bigger values of x give smaller weights. They're worth less. They're more uncertain. And that should make sense. Maybe the variance function is proportional to the mean function. And that's what this says here, that the variance of y is a proportional function to the average value of y as a function of x. And so we could inversely weight and give weights to inverse of the mean function. We could also attack and solve this problem with transforming variables, which we'll learn about in an upcoming unit, not in this one. Here's a little example from some apple trees. We have data where we are keeping track of the average number of stem shoots. That's the response. The number of stem shoots that are happening over days of growing. And so days of growing is the predictor variable, and the number of stem units is the response variable. And every one of these points represents an average of differing numbers of plants. And so the differing numbers of plants that every observation is based on is in the data set as little n. And so little n will form our weights, day will be our predictor variable, and y bar, the average stem units, will be the response. And you will invoke weighted least squares by this kind of a structure. It's still the lm command. You use the response y bar as a function of day, but you specify that the weights are equal to n. And that has to be a variable that is in the data set. We have this variable in the data set, and it's called n. If you would need to use weights for some other kind of variable or other kind of function, you need to make the variable in your data frame. You will see that in the homework assignment where we use a function and we have to make the variable that matches it. Anyway, here is the estimated intercept and the estimated slope and the standard errors for the weighted least squares. If, for example, you wanted to do a prediction for a weighted least squares model, it works very similar to how you would do predictions for ordinary least squares, except notice that in the standard error formula, you have to use and supply an appropriate weight. What weight do you want to give the observation? You have to specify more than just what value of x or what vector of x you want to predict at. X star, x subscript star is the conditions under which you want to predict. not only do you have to specify that, but you have to specify the weight for the observation as well. And in terms of the apple tree data, we're going to try to predict at day 35, but we also are going to specify that the observation that we're trying to predict is made up of 10 plants. And so you have to specify the weights inside the predict command when you use weighted least squares. In ordinary least squares, all the weights are all the same and it doesn't matter. But for weighted least squares, you have to specify the appropriate weight. Remember, in this command, the estimated STEM units would be 17.58, and this would be the appropriate prediction interval. If you do a residuals analysis from weighted least squares, you can do a residual plot like I've done here. The problem is that when you do weighted least squares, it's usually suggested by statisticians that you use weighted residuals according to the square root of the weight. So you would take your ordinary residual, y minus y hat, but multiply it by the square root of the weight for that observation. Those kind of residuals are called Pearson residuals. And again, for ordinary least squares, it doesn't really matter, but when you do weighted least squares, it is suggested to use these weighted Pearson residuals. And I've given the residuals command with the option residuals Pearson, type Pearson, to get appropriate residuals. You can make a habit of just using Pearson residuals, and it will be a safe and suggested thing to do. Another really common place where we use weighted least squares is when we analyze survey data. Because in survey data, a single observation is probably trying to represent maybe 3 to 100 observations maybe back in the population. And so survey data usually comes with survey or sampling weights. And I've denoted that here by the symbol pi to represent the sampling weight. And it turns out that when you analyze survey data with sampling weights, the right thing to do is to use these pi's as the w's in weighted least squares regression. That's something to file away in your memory bank for when you analyze data that come from designed surveys. Okay, what happens if we don't really do quite the right thing and we use ordinary least squares in the case where maybe weighted least squares was the right thing to do, but we didn't do it? What would happen? What would go wrong, essentially? Well, it turns out that the standard error for the beta hats will use the wrong thing. This will be the variation and not the variation from the OLS estimates. And so if you're worried about possibly doing the wrong thing, what has been suggested is to use a correction when doing ordinary least squares, and maybe you're worried about, maybe you should have used weighted least squares. What you can do is you can use the observed residuals to correct your variance matrix, and it will produce new standard errors that you can compare to the old ordinary least square standard errors and observe the kind of impact that you would get between the two approaches. And the approach for modifying the variance matrix is called a sandwich estimator. And here is an illustration of doing it. We have some data in our textbook about a machine that checks for vapor when you fuel up your car with gasoline. The data set is called Sniffer, and we're going to use the amount of hydrocarbons that are detected as a function of all the values, all the predictors in this data frame: tank temperature, gasoline temperature, tank pressure, gasoline pressure, and this would be the ordinary least squares model for such data. If you wanted to invoke a sandwich estimator, you'll need to install the LM test package library and then use the coef test option onto that model, modifying the variance covariance matrix with the option HCCM, and you'll get exactly the same kind of estimates, but the standard errors will be modified. You'll notice these standard errors are ever so slightly different. Well, maybe somewhat substantially different for gas pressure and tank pressure. And you might want to consider a different kind of reporting of results in the standard errors based off of using a safer estimate of the variance function. One way to test for non-constant variance is to use some of the testing methods which we'll develop here. And we're going to rewrite the variance function as sigma squared times e raised to the lambda z. And z is going to be some variables, maybe regressors and things in our data. These will be observed data items. Maybe the response vector, maybe regressors, something like that. And lambda is a parameter vector which will control which or what parts of the observed data will change the variance function. Notice that when lambda would be 0, e to the 0 is 1, and you would have a constant variance function. Whenever lambda is not 0, you will get a changing variance function as a function of whatever z is. So z might be the response variable, it might be a predictor, it might be measuring space or time in which we measure something. And so this variance is always going to be greater than 0 because this e function is always going to be a non-negative value. And the variation is going to depend on z through, z and lambda through this linear combination. This would mean lambda 1 times z1 plus lambda 2 times z2. That's what this linear combination would mean. And the variance is monotonic. It's typically going to go up or down as a function of the components of z. As I talked about previously, lambda of 0 is going to mean that the variance is constant. So you might be thinking about doing a test like this. Let's think about just a simple case of lambda being 0, constant variance. Lambda not 0 means non-constant variance. And how might you do a test? Well, essentially what you do is you take the residuals from a model that doesn't include any non-constant variance. You assume the null hypothesis is true. You get the residuals, and then you make a new variable out of them, ui, which is the square, sort of the scaled squared residual. And what you do is you observe whether these squared residuals are changing as a function of z. And of course, if the variance is non-constant, the squared residuals are going to go up or they're going to go down as you change across z. And we develop a statistic for this, and there are functions built for R to do tests like this. So here's a little example. This is from some financial and corporate data from Canada. The response variable interlocks mean how many boards of directors do the members of your company's board of directors serve on. So higher interlocks mean that your board of directors are serving on higher numbers of other companies' boards. So it's a measure of diversity of corporate governance. And how is that value a function of assets, the kind of sector of business, sector would be a factor variable, and what nation the company belongs to. I think it's Canada, US, or UK. And if you fit that kind of multiple regression model into an object called ORNMOD, you will see typical Pearson residual pattern of non-constant variance. And so you can use the NCV test command to calculate non-constant variance tests. And so for this model object, if you just give NCV test the data multiple regression object as an argument, it's going to compute non-constant variance as a function of the mean function. and the test statistic is nearly 47. The degrees of freedom is 1. There's one linear function in the variance function, and the p-value for this test is amazingly small. And that suggests very strong evidence that the variance is non-constant as a function of the mean function. And we saw from the residual plot that it is very clear that as the estimated interlocks or the mean function goes up, the variation is going up. And that would be an example of testing non-constant variance as a function of the mean function. If you wanted to do non-constant variance testing in terms of the components or the parts of the problem, you would need to separate out the parts of the lambda vector that you want to consider in the null hypothesis and the parts of the lambda vector which would be involved in the alternative. In this case, for example, I'm going to examine the null hypothesis. Let's see. I'm going to examine the null hypothesis that the non-constant variance or the variance function is a function of only assets in the null hypothesis. And in the alternative hypothesis, I'm going to let the non-constant variance be a function of all three of these variables. So this is a nested null and alternative, and I want to compare the data evidence to suggest, do I need the more full function for the non-constant variance, or is it solely a function of just assets? Do I need the additional two sets of regressors, the additional two regressors to explain the variation pattern? And what you do is you fit two models. You do two non-constant variance tests. You do one where the variance is a function of only assets, and then you do another one where the variance is a function of both assets, all assets, sector, and nation. And then you do a subtraction of the two test statistics, and then you do a p-value using the chi-square test. And so here's how we did that. We do the non-constant variance test for the alternative hypothesis that says that the variation is a function of wiggle, function of assets, sector, and nation. We get this chi-square statistic and 13 degrees of freedom. For the null hypothesis model, we say that the variation is only a function of assets, and so we get the chi-square statistic, 20.17, and 1 degree of freedom, because assets is just one quantitative variable. If we want to do the comparison of the null and the alternative, we need to subtract the two chi-square statistics from each other to get a subtraction. We need to subtract the degrees of freedom from each other to get 12 degrees of freedom. And then we need to use the PCHISQ command for the test statistic, the new degrees of freedom. Lower tail equals false basically means we need to find the upper tail probability, and that would give us the right p-value for this test as I've gone through on this overhead. And so the final result is a very small p-value suggesting very strong evidence for the alternative hypothesis that the variance function is a function of more than just assets. It's a function of also sector of industry and nation, that those additional pieces help understand and are part of the variance function. When we have variance patterns in the errors, and we have a variance function sigma, capital sigma, that would suggest that we need weighted least squares, it frequently turns out that this sigma matrix has frequently occurring and commonly occurring patterns, and we can learn how to handle those kinds of patterns and do a better job on modeling common patterns and problems. Here are some of the basic sigma error variation correlation patterns. The usual one is just independence, and every observation is uncorrelated from every other observation. That's what number 1 means. That's the common assumption we've been going on up till this chapter. There's a correlation pattern called compound symmetry that I would want you to know about. First order autoregressive, you need to know about that because a lot of times observations are measured on the same unit but at different time points. And what first order autoregressive means is that the correlation will change depending on how far apart in time the measurements are being made. So if I is time period 2 and J is time period 1, those time periods are 1 unit apart, and so the correlation between them is rho. But when observations might be 5 units apart, the correlation between those observations would be rho to the 5th power. And rho is a correlation. It's between -1 and +1. And when you raise something that's under 1 to the 5th power, it will shrink and it will be a much smaller value towards 0. And so correlation will decrease as the measurements get farther apart. Block diagonal can happen when observations are taken within a grouping, and if they're similar within a grouping, they will form blocks of similar measurements. Here's what a sigma matrix looks like for complete independence. The first observation has variance sigma squared, and it has no relationship to the second observation or to the third one. The second observation has variance sigma squared. The third observation has variance sigma squared, and no observation is correlated with any other observation. Compound symmetry says that every observation has a correlation rho with every other observation in the data set. And this can happen when you are measuring students that are all in the same classroom. Well, every student in the classroom will have the same correlation with each other because of the same environment and the same teacher and the same textbooks. Compound symmetry happens very frequently. Every observation, same correlation with every other. AR1, autoregressive 1, as I mentioned, is usually done with respect to time patterns, and what you might have are repeated measures on the same subject or person or animal. And what this says is that measurements that are 1 unit apart in time have correlation of rho. Measurements that are 2 units apart in time have correlation rho squared. Just compute this for yourself. Just let correlation be 0.9 between successive measurements. 0.9 to the first power is just 0.9. But 0.9 to the second power is something smaller. It's 0.81. And 0.9 to the third power is going to be even smaller. And so you get this declining correlation as you move further apart in time. Sometimes what we have are more complicated structures where we maybe have a relationship between a regressor X and a response variable Y. But we might have observations and repeated observations on the same unit. So we might have a particular animal or person or company with many measurements X and Y, and a scatter plot of points could be done for every unit. And so this is a special kind of data situation which you haven't seen before. Usually we've always had one observation on X and Y per unit, but in this case that I'm describing, we might have more than one measurement on a person or on an animal. And you might do a graph for these points for every subject, and you might observe something like a straight line for every person, but the intercepts and the slopes might differ across people. If I skip ahead a couple of graphs, you might see this here. You know, each one of these lines is for a different subject, and you can see that there is possibly, well, certainly different intercepts for every subject, and maybe slightly different slopes for every subject. And so this kind of a structure will amount to needing different kinds of methods and thinking. So we might specify a model like this one, a y observation for the ith unit, and the jth measurement on the ith unit might be related to x like this. We might have an overall intercept piece plus an overall slope piece times the value of x plus random error. Well, let's talk about these betas and little b's a little bit more detail. So this is kind of a linear regression model with random error. What do these things mean? Well, little b naught I and little b 1I are going to measure individual variations in intercept and slope for subject I. It's almost like drawing a random draw from an intercept pool that will modify the intercept around an overall intercept of beta naught. So you might think of beta naught as the overall intercept for an entire population. And beta naught I is sort of a randomly shifted amount above or below this population intercept, just for the ith person. Similar sort of thinking about slope. We might have a population average slope, beta 1, but then little differences in slope for every person, b1I. And in this kind of formulation, we would call the betas fixed effects, and we'll call the little b's, these random shifts in slope or intercept, random effects. And when models have both fixed and random effects, we call them mixed models. And we need special software and special kinds of considerations for analyzing data like this. Here's an example of some data that might be like this. We randomly assigned some students to 3 different exercise programs. One of them had weightlifting, where the number of repetitions or the number of exercises repeated goes up. The other group had the amount of weight that you lift would increase. And the third group didn't have any exercise intervention, and what we did was studied the strength of the subjects over a time period. And so we have individual profiles. This panel here for control, you can see that there's variations in the intercept and almost no slope across time. The strength for these subjects doesn't look like it changed at all. It's pretty much constant, like how it started. For the repetition increase, it looks like there's a lot of variation between people, but a little bit of evidence of upward trending. Same thing for the profiles for the weight increase. Might be good for a model like this. Here's a data situation where individual people were given audio signals of different loudness, 50 to 90, and then they were asked to express how loud it was that the sound they heard, and they expressed that through a segment length, which is the response. And you can see that pretty much everybody was hearing something. As the signal was louder, they tended to agree that it was louder, but the variation in the intercepts and the slopes is possibly considerable. So how can we model y as a function of loudness and yet have differing intercepts and differing slopes? We're going to need the LME4 package and the LMER function to do this, and we are going to specify fixed effects, the beta naught and the beta 1, by saying that y is a function of the loudness, and this part of the model will make a beta naught and a beta 1 term. Random effects are specified through parentheses terms, and this says, this is kind of compact notation that says, let there be an intercept change by subject, a b naught I, and a slight slope adjustment, in other words, modify the loudness effect, b1I. And so random effects are specified through parentheses terms, fixed effects are specified through terms that don't have parentheses, and you can get a model estimate here. And so here are the fixed effects. Here you can see very clear evidence for increasing response with increasing loudness. This would be beta 1 hat. Beta naught hat is this negative 3.2. The random effects are in this random effects section, and you can see that the standard deviation for the B naught terms is pretty substantial. It's a 1.135. So a lot of intercept variation relative to the variation between the slopes. You'll notice that this loudness standard deviation is saying that, well, there are slight differences in slope by subject, the B1I terms, but not very much variation in the B1I terms. And that's how you would use a mixed model. Sometimes we can handle non-constant and changing variations by simply transforming the y variable or the response. And common ones are doing something like the square root of y, and you would use the square root of y when the variation is proportional to the mean function. A more extreme transform is the log or logarithm of y, and you would use that when the variation is proportional to mean squared. When the variation is going up more quickly than just proportional increase, you might use log. When the variation is even more extreme than that, you can use the inverse function y to the negative 1 power. So you have an inverse transform of y. Another possibility that you might see is the arcsine square root function. Typically, biologists have historically sort of used this kind of strange transform to deal with y measurements that are proportions. And statisticians don't suggest that you do this, that you learn about logistic regression to do this kind of data analysis when you have proportions. The text got cut off here, but transforming y to remove non-constant variance might change the curvature of the mean function, and so you got to be careful when you do this. The delta method is a very good way to come up with variations for complicated estimates or complicated functions of estimates. So sometimes we have complicated functions of the betas that we want to have variances for, and the delta method is a way to get variances for things that are difficult to obtain by other methods. And there is a delta method function in R that will do this. As an example, consider the transaction data where we have type 1 and type 2 transactions trying to explain teller time. And we have an ordinary least squares model like this. And I'm interested in a ratio of the betas. Beta 1 divided by beta 2. Or in other words, how many type 1 transactions, well, how many type 2 transactions does it take to, well, I guess it's really, what's the relative time that it takes to do a type 1 versus a type 2 transaction? If that fraction is 1, they're equally time consuming. If the fraction is 2, it means that type 1s are double the time of type 2. So it's a way to specify a ratio. And ratios are hard to estimate. Well, they're not hard to estimate. You just divide the two estimates. But what's hard is the variation. And so a way to get a variation for a ratio of estimates is to fit the model and do delta method of the model object, specify the function of the terms you want. We want T1 divided by T2, and we get an estimate, and it shows that type 1 transactions are almost 3 times as lengthy as type 2s, and then here's the variation. And so this is a very useful method for coming up with variances. So you can see that the reasonable range is about 2 to 3 times longer for a type 1 than a type 2 method. Another way to get variations is from a method called the bootstrap. And the bootstrap is a way where we use the data set we have to come up with variations. And the key to this is to realize that instead of resampling again from the population and drawing new data, we can resample from our existing data set and approximate the variation back in the population from the variation drawing from our sample data. And so what we do is we repeatedly take new samples from our sample data in order to get the right amount of calibration on the variation. And so what we can do is estimate our same transaction model and then specify a function, I've called it here fun, that takes the first estimate, it's actually the second coefficient in the vector, and dividing it by the third coefficient in the vector. Remember, that would be beta 1 divided by beta 2, the estimates. And then implement the boot function, which says use our model estimates, compute, so draw new data, compute new model estimates, and then from the model estimates divide them as I've specified in fun, and do that for 800 random draws from our data set. And then summarize what we get. Well, it turns out that the median of our bootstrapped estimates is about 2.67. The variation in our bootstrap estimates is about 0.52. And if we wanted a confidence interval, here would be the confidence interval we'd get from the bootstrap. And you could compare that to what we got from the delta method, and the bootstrap looks like it's fairly similar on the estimate, but the variation for the bootstrap was quite a bit bigger than it was for the delta method. But it's another way to get estimates and variations. Here's a picture of the 800 bootstrap estimates. You'll notice they typically are hanging around 2.6, a ratio of about 2.6 times the time that it takes. It takes 2.6 times more time to handle a type 1 than a type 2 transaction. And you can see the variation in those bootstrap estimates.